Hello everyone, I'm Jhon Cabalbag and I'm here to report to you the industrial wastewater treatment. But before that, what is industrial wastewater? Industrial wastewater are the liquid waste coming from the manufacturing facilities or industrial plants which uses water as their medium to produce their product. What is industrial wastewater treatment? Industrial wastewater treatment describes the processes used for treating wastewater that is produced by industries as an undesirable byproduct. After treatment, the treated industrial wastewater or effluent may be reused or released to sanitary sewer to a surface water in the environment. What are the sources of industrial wastewater? First is the battery manufacturing. Battery manufacturers specialize in fabricating small devices for electronics and portable equipment such as the power tools or larger high-powered units for cars, trucks, and other motorized vehicles. Pollutants generated at manufacturing plants include includes cadmium, chromium, cobalt, copper, cyanide, iron, lead, mercury, nickel, oil and grease, silver, and zinc. Next is the electric power plants. We have lots of electric power plants here in the Philippines, but fossil fuel stations, particularly the coal-fired plants, are a major source of industrial wastewater. Many of these plants discharge wastewater in significant levels of metals such as the lead, mercury, cadmium, and chromium, as well as the arsenic, selenium, and nitrogen compounds. Another is the food industry. Wastewater generated from agricultural and food processing operations has distinctive characteristics that set it apart from common municipal wastewater managed by public or private sewage treatment plants throughout the world. It is biodegradable and non-toxic. In the food industry includes the dairy processing plants which generate conventional pollutants, and also in the animal slaughter and processing produces very strong organic waste from body fluids such as the bloods and gut contents. And also in the food processing activities such as plant cleaning, material conveying, bottling, and product washing creates wastewater. Next is the iron and steel industry. The production of iron from its ores involves powerful reduction reaction in blast furnaces. Cooling waters are inevitably contaminated with products, especially ammonia and cyanide. Although many plants operate acid recovery plants, particularly those using hydrochloric acid, where the mineral acid is boiled away from the iron salts, there remains a large volume of highly acid ferrous sulfate or ferrous chloride to be disposed of. Many steel industry wastewaters are contaminated by hydraulic oil, also known as the soluble oil. Another sources of industrial wastewater is the mines and quarries. The principal wastewaters associated with mines and quarries are slurries of rock particles in water. These arise from rainfall washing exposed surfaces and whole roads, and also from rock washing and grading processes. Volumes of water can be very high, especially rainfall related arising to large sites. Some specialized separation operations, such as coal washing to separate coal native rock using density gradients, can produce wastewater contaminated by fine particulate, hematite, and sulfactants. Oil and hydraulic oils are common contaminants. Next is in the nuclear industry. The waste production from the nuclear and radiochemicals industry is dealt with as radioactive waste. Organic chemicals manufacturing. The specific pollutants discharged by organic chemical manufacturers vary widely from plant to plant, depending on the types of pollutants manufactured, such as bulk organic chemicals, resins, pesticides, plastics, or other synthetic fibers. Petroleum refining and petrochemicals. Pollutants discharged at petroleum refineries and petrochemicals plants includes the ammonia, chromium, phenols, sulfides, and other conventional pollutants such as the biochemical oxygen demands, oil and grease, and suspended solids. Next is the paper and pulp industry. This industry, for their mills with high inorganic loadings like salt, tertiary treatments may be required, either general membrane treatments like ultrafiltration or reverse osmosis, or treatments to remove specific contaminants such as nutrients. Another sources is from the textile mills. Textile mills, including carpet manufacturers, generate wastewater from a wide variety of processes, including wool cleaning and finishing, yarn manufacturing, and fabric finishing such as bleaching, dyeing, resin treatment, waterproofing, and flame proofing. Pollutants generated by textile mills includes the BOD or the biochemical organic demand, oil and grease, sulfide, phenols, and chromium. After knowing these sources of industrial wastewater, next I will discuss to you on how we treat this industrial wastewater. First is the brine treatment. Brine treatment involves removing dissolved salt ions from the waste streams. Although similarities to seawater or brackish water desalination exist, industrial brine treatment may contain unique combinations of dissolved ions such as hardness or other metals, necessitating specific processes and equipment. Brine treatment technologies may include membrane filtration processes such as reverse osmosis, ion exchange processes such as electrodialysis or weak acid cation exchange, or evaporation processes such as brine concentrators and crystallizers employing mechanical vapor recompression and steam. Next treatment is the solids removal. We all know that industrial wastewater is a mixture of solid and a liquid. And on this, most solids can be removed using simple sedimentation techniques with the solids covered as slurry or sludge. Very fine solids and solids with densities close to the density of water pose special problems. In such case, filtration or ultrafiltration may be required, although flocculation may be used using alum salts or the addition of polyelectrolytes. And reducing solids such as waste product, organic materials, and sand is often a goal of industrial wastewater treatment. And some ways to reduce solids include primary sedimentation or the clarification, dissolved air flotation, belt filtration, or the micro-screening and the drum screening. Next is the oils and grease removal. The effective removal of oils and grease is dependent on the characteristic of the oil in terms of its suspension, state, and droplet size, which will in turn affect the choice of separator. Oil in industrial wastewater may be free light oil, heavy oil, which tends to sink, and emulsified oil, often referred to as soluble oil. Emulsified or soluble oils will typically require cracking to free the oil from its emulsion. In most cases, this is achieved by lowering the pH of the water matrix. One equipment used to separate the oil and water is the API separators. From the picture, it is a typical API oil-water separator which is used in many industries. Based on the picture, the industrial wastewater passes through the inlet and passes through the trash trap, which is the inclined rods, and then passes through the oil retention baffles, which separates the oil and water. And it has an adjustable overflow weir, sludge sump, and the chain flight scraper, and then passes through the outlet for the next process. The API separator is a gravity separation device designed by using the Stokes law to define the rise velocity of oil droplets based on their density and size. The design is based on the specific gravity difference between the oil and the wastewater, because that difference is much smaller than the specific gravity difference between the suspended solids and water. The suspended solids settles at the bottom of the separator as a sedimented layer, and the oil rises at the top of the separator, and the cleansed wastewater is the middle layer between the oil layer and the solids. Another type of separator is the parallel plate separators. It This is similar to API separators, but they include tilted parallel plates assemblies, also known as parallel packs. The parallel plates provide more surface for suspended oil droplets to coalesce into larger globules. Such separators still depend on the specific gravity between the suspended oil and the water. However, the parallel plates enhance the degree of oil-water separation. The result is that the parallel plate separator requires significantly less space than the conventional API separator to achieve the same degree of separation. Next process is the removal of biodegradable organics. Biodegradable organic material of plant or animal origin is usually possible to treat using extended conventional sewage treatment processes, such as the activated sludge or trickling filter. Problems can arise if the wastewater is excessively diluted with washing water or is highly concentrated, such as undiluted blood or milk. The presence of cleaning agents, disinfectants, pesticides, or antibiotics can have detrimental impacts on treatment processes. From the removal of biodegradable organics, activated sludge process is used. Based on the picture, it is the generalized diagram of an activated sludge process. An activated sludge is a biochemical process for treating sewage and industrial wastewater that uses air or an oxygen and microorganisms to biologically oxidize organic pollutants, producing a waste sludge or flock containing the oxidized material. In general, an activated sludge process includes the aeration tank and the settling tank. Next is the trickling filter process. A trickling filter consists a bed of rocks, gravel, slag, peat moss, or plastic media over which wastewater flows downward and contacts a layer of microbial slime covering the bed media. The fundamental components of a complete trickling filter system are a bed, an enclosure or a container which houses the bed of filter medium, a system for distributing the flow of wastewater over the filter medium, and a system for removing and disposing of any sludge from the treated effluent. Next treatment is the removal of other organics. Synthetic organic materials including the solvents, paints, pharmaceuticals, pesticides, and products from coke production and so forth can be very difficult to treat. Treatment methods are often specific to the material being treated. Methods include advanced oxidation, distillation, absorption, ozonation, vitrification, incineration, chemical immobilization, and landfill disposal. Some materials, such as some detergents, may be capable of biological degradation, and in such cases, a modified form of wastewater treatment can be used. Next is the removal of acids and alkalis. Acids and alkalis can be usually neutralized under controlled conditions. Neutralization frequently produces a precipitate that will require treatment as a solid residue that may also be intoxic. In some cases, gases may be evolved requiring treatment for the gas stream. Some other forms of treatment are usually required following neutralization. Last treatment used in the industrial wastewater is the removal of toxic materials. Toxic materials, including many organic materials, metals, acids, alkalis, non-metallic elements, are generally resistant to biological processes unless very dilute. Metals can be often be precipitated out by charging the pH or by treatment with other chemicals. Many, however, are resistant to treatment or mitigation and may require concentration followed by landfilling or recycling. Dissolved organics can be incinerated within the wastewater by the advanced oxidation process. And one of the technology used is the molecular encapsulation that has the potential to provide a system for the recyclable removal of lead and other ions from polluted sources. And that ends my presentation. But to sum it up, the purpose of industrial wastewater treatment is to treat and clean the polluted water and to remove the chemicals and other organic compounds that can be used in our daily necessities.